Well, howdy, 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 howdy there, folks. Mr. Dorfler back at it again for section 2 of Newton's laws. Now, remember that this will be the last section before our quiz. So what you're doing today needs to be completed before tomorrow when you come back into class, because you have homework, first of all, and you are going to have a quiz when you come back. So make sure you watch this and do the homework. It's going to help you, okay? If you are a remote student or absent or quarantine, I'm sure that list is going to change from right now, the moment I'm making this video, until last time. But whatever the result is, I will be making a, a digital or a Google form version of it, of the quiz, whenever we do this, so you can take it at home. Sounds great? All right. Wait until the end of this video. I'm doing a little sneaky on you, because I will then give you what homework numbers need to be completed for your problem bank B. And if you email me or message me, I'll know you didn't watch the entire video. Ha ha ha. All right. So anyway, we're going to be talking about Newton's first law. This whole chapter is about Newton. This whole semester thus far, we've been talking about motion of objects. And now we need to see, what does that motion of an object carry in terms of force? And so we're going to be checking out all of Newton's laws throughout this chapter. And pretty interesting, okay? We're taking it a step up from when you first heard about Newton's first laws and how we could calculate them back in the intro, okay? These are going to be a little more technical, but it's involving things that you've already really done, okay? So don't let some of the questions, confuse you, because really what we're really going to be doing are resolving components, the x and y components, bringing back Pythagorean's theorem, using the inverse tangent, okay? The thing is, though, we have to compare, in certain instances, we have to compare the vectors that we resolve, compare them to vectors that are going to be a force in this scenario. Okay, so that's why using free body diagrams to help us envision and align those vectors, those forces, is going to be a big deal. It's not required of you to make a free body diagram. It is just helpful. Okay, and again, I'm going to show you some of my amazing artwork once we get into some of the practice problems here. Okay. All right, so in this section, we are going to explain the relationship between the motion of an object and the net external force acting on that object. Remember, when we say net external force, is there a net external force that's going to cause the change of motion or acceleration or state of an object? Okay, if not, then we say what's called an equilibrium. We'll talk about towards the end of this section. We'll then determine the net external force on an object. So there's where our calculations come in. And we'll also calculate the force required to bring an object into equilibrium. Okay. We don't necessarily do that. We typically stick with the net external force on an object, determine what those are going to be, whether or not an object is going to remain in its current state of motion or its motion will change. Okay. Which, the last two bullet points kind of do go hand in hand together. So that video right here talks about Newton's first law of motion in the science of NFL football. I don't want to take up any more time. You can look it up. You can see the title of the video in there. It's only about 6 minutes long or so, but you can do that on your own time. Okay, it's just a neat thing to talk about Newton and sport that I would say probably a good number of us do like. Not everyone likes it, but it applies to a lot of real life situations anyway. So take a peek at that if you want to. Anyway, Newton's first law states that an object at rest remains at rest, and an object in motion continues in motion with constant velocity, that is, constant speed in a straight line, unless that object experiences a net external force. So going back to the middle school days, object at rest stays at rest, and object in motion stays in motion. Adding on to it now that we are high schoolers, it remains in those states unless we have a net external force acting on that object that's going to change its current state. So when the net external force on an object is zero, the object's acceleration or the object's velocity will also remain zero. It refers to the net force on an object, meaning Newton's first law. So the net force on an object is going to be a vector sum of all the forces acting on the object. And it can be found by using methods for finding resultant vectors. What we did last chapter. It's all coming back now. So if we look at this image on the car here, the car is sitting on a flat surface, okay? So although several forces are acting on this car, the vector sum of the forces is 0. Now, granted, we are not told what the magnitude of the forces are in, numerically speaking, but if we really wanted to, we could measure each one of these vector forces and their size, their length of each vector should be equivalent for the opposing forces, meaning the air resistance here, or the resistance of friction, sorry, so that could mean a lot of stuff, like from the road or the wind, and the forward friction, okay, the forward force, they are going to be equal yet opposite, okay? Same with the force of ground on the car, which is the normal force pushing the car up, and the force of gravity, which is going to push the car down to the center of Earth. And again, also important note that you see where all the origins are starting from is right in the center of the object, okay? Now, again, these two vertical forces are going to cancel each other out. These two horizontal forces are going to cancel each other out. Only if we have an imbalance in these forces will we see a change in the motion. So if this car is going forward, then the acceleration or the velocity of this vehicle will remain unchanged because there is a net sum of 0 on this car. If we were to change any of these, then we would have a change in motion. Okay, so it all depends on if we have what's called equilibrium or not. And so we're going to come back to Derek in his physics book here in just a moment. I want to talk to you about a couple things about inertia and equilibrium. Now, oftentimes, Newton's first law is considered to be the law of inertia, okay? Because it states that in an absence of a net force, a body will preserve its state of motion. But what is inertia? Well, inertia is the tendency of an object to resist being moved, or if the object is moving, resist a change in a speed or direction, okay? And so I always like to use this if you are driving on the interstate and you get on the exit ramp. A lot of times those exit ramps are going like this. That's in an effort to slow your vehicle down. But, if you're going onto the exit ramp and you hit that first turn, a lot of times your body wants to continue going in that straight line. Okay, even though the car's turned, your body wants to go in that straight line in its original direction. So that's why you tend to lean side to side, depending on which way you're turning, because your body wanted to continue moving in that original direction. Now, mass, is a very important measure of inertia. Think about a semi-truck compared to a sports car. The semi-truck has a much larger mass, and therefore it's going to have a much more difficult time changing its state of motion because it has to counteract all that mass as being moved. So, again, mass is a huge component of a measure of inertia. Now, another useful tidbit of information for inertia is the seatbelt. Okay. Well, we just said, oftentimes inertia is going to cause us to move forward, backward, left, right, whatever. Inertia is what's going to help lock in your seatbelts. If you look at this illustration over here, we have a very basic mock-up of what a seatbelt system looks like, where we have a large mass that is located on or positioned on tracks. We have a pin that connects a rod and a ratchet and pulley system. So your seatbelt is attached to this ratchet and pulley system. And as you brake, or the harder you brake, this large mass, because of inertia, is going to want to continue going towards the forward portion of the seat. When it does that, it rocks this rod back into that ratchet system. And so when it goes forward, this rod goes into this ratchet system, locking the seatbelt in place. So that's what's happening when it locks. Okay, you have this system that is locking it, so you stay belted against the car seat. So using physics to help physics, using physics to help a system keep you from going forward out of your seat. Amazing, right? I mentioned the term equilibrium a little bit ago. It's a state in which the net force on an object is zero. When an object is either at rest or moving with constant velocity, then we say it's in equilibrium. And Newton's law also can describe equilibrium. And to determine whether a body is in equilibrium or not, you need to find the net force. If the net force is zero, the body is therefore in equilibrium. If not, then a second force equal and opposite to this net force will end up putting the body into equilibrium. And that could be one of numerous things, okay? So let's go back to Derek and his textbook. Now, here, what we're going to do is a few things in this type of problem, okay? But it all really comes back to resolving the vectors. So stay with me here. So Derek leaves his physics book on a top of a drafting table. If you don't know what a drafting table is, it was a table that could be a very large table, actually, that could be lifted up and angled. So almost kind of like an artist's thing where they could do blueprints and any other engineering or drafting work that needed to be done. So that's why it's large, because you need to have many images that you would draw, like blueprints on there. Drafting tables are kind of obsolete anymore with the advent of computer-based drawing programs. But my dad was an engineer before he retired a couple years ago, and he always had a drafting table. A lot of the old school engineers still like to have a drafting table in their office just because that's what they grew up working with. And so I used drafting tables for a while whenever I go and work with them. So I know what they're talking about. But I know a lot of kids these days may not know what a drafting table is. So back at the question. The drafting table is inclined at 35 degrees. The free body diagram below shows the forces that are acting on the book and find the net force acting on the book. So really, what we want to determine is what will happen to this book if Derek has just simply left his textbook on this table at this certain degree. Okay? So see here, we've got the book, and we've got the table, kind of got the tannish color, and we've got the vectors here. We've got the force of friction, which is going upwards the table. It's what's trying to hold the book there, and it has a force value of 11 newtons. You have the force of gravity on the book, which is acting straight down, okay, from the center of the book at 22 newtons. And then we have the force of the table on the book. So the force that the table is applying against gravity essentially is 18 newtons. Okay? Again, that will always act perpendicularly to the surface upon which the object resides. Okay? So that's why we have it going this way. So don't get caught up. Because this table is at an angle, this force of the gravity isn't necessarily going to be the actual force acting in total on the book. Okay? This is what gravity on the book's doing, but because of this angle, all 22 newtons may not actually be acting on that book. So what we need to do is a few things. There's going to be a few tips that we need to do when we are setting these up. Okay? First of all, list what we're given. We're trying to figure out the net. We're trying to figure out the net force in both the X and the Y, so both the horizontal and the vertical directions. Okay? So we need to choose an axis system. And so we need to choose it to where as many of the vectors lie on our X and Y coordinates. So right here, if we rotate the axis, the X and Y axis, to line up on as many of those vectors as we can, where we have the force of friction on the X and the force of the table on the book in the Y. That's 2 of the 3 vectors that we were given. So that's a good setup here. Okay. So what we need to do, we need to figure out what the vertical and horizontal components or vectors will be in this situation. So we're going to be focusing our attention onto this downward force of gravity of the 22 newtons, okay? Because we need to figure out the downward force and the force acting to the right, okay? So here's what we also need to remember. This book is not at the 35 degree mark, okay? This book is located at the third angle. If we create a 90 degree angle, which this is always what happens, okay? The top of the table gets at an angle, and then there's always a base of the table. So it's hinged right here at the bottom, so that's where you get the 35. But the book is up here. So this is where our theta is going to be. So we have to figure out what that angle is. So if we know that this is a right triangle, that's 90, that's 35. We sum up those two values and subtract them from 180, and we get a total of 55 degrees for our theta here. So in order to calculate the vectors in the x and the y, we got to go back to cosine and sine. So we're going to use cosine of theta to solve our x, and we use sine of theta to find our y, our vertical component. So we have to solve for the x component here, okay, and the y component here. So we have to rearrange this equation to where we get the vector in the x direction equals the force of gravity on the book times cosine of theta, and the force of gravity in the y direction is we're going to use the force of gravity on the book and the sine of theta. Now, I want to call to your attention something real quick. I don't know why, and I can't change these. Okay, these are images that are laid into this slide that the book made. If I were you, I would cross this x where my mouse is and this x out and replace them with y. Why they went back, no pun intended, why they changed this from y to x, I don't know. They done and goofed up. So these over here, these two x's that you're solving for should be the y because you're solving for the vertical component. So you're going to take the force of gravity on the book, which is 22 newtons, we're solving for x, multiply by the cosine of 55, and we get a vector sum or a vector value of 13 newtons in the horizontal direction to the right. Do the sine over here for the y, we get 18 newtons. Okay, so that means that there are 18 newtons actually acting in the vertical direction here, downward, and there are 13 newtons acting in towards the right direction. Okay, so now we have to figure out what does that mean. So in the x direction, we have to compare, as I was mentioning earlier, we have to compare the vector values. And so after we put in our newly calculated vector quantities here, 18 in the vertical downward, 13 to the right, and compare them. So 13 newtons minus 11 newtons, okay? We get an overall difference of 2 newtons. In the y direction, we have 18 newtons in the vertical upwards and 18 newtons in the vertical downwards. So they actually have a net 0 in the vertical direction, which is good because our book isn't flying off the table and it's not going through the table. So we would expect the verticals to pretty much cancel each other out. But we do have a difference in these vector values here. We have a greater vector amount on the right. So we do not have a net 0 in the horizontal. So what that means is because we have a greater force value, a greater force difference to the right in this scenario, Derek's book is going to slide down the table. Okay, there's not enough frictional force to keep it in its current location at that angle of 35 degrees. So since there is a net force of 2 towards the right, the book will accelerate down the incline. Okay, so let's look at a couple of other examples here before I call this video. I want you to open up your books to page 128. Okay, 128. While I do that, I'm going to open up and get my camera ready. Okay, on page 128. Excuse me, we're going to do the 3 questions here. So we have, let me get the book over here. Number 1, under practice B on page 128, says a man is pulling on his dog with a force of 70.0 newtons, directed at an angle of positive 30 degrees to the horizontal. Find the x and y components of this force. Now, we don't necessarily have to draw anything out there. If we want to, you could, but we don't have to. So we know that he's got a force of 70 newtons and a theta of positive 30.0 degrees. Excuse me. So if we need to figure out our vectors, we just simply take f of x times F of Y. We take the force that was going to be 70 newtons, multiply it by cosine of theta, and then for Y, we do the same thing, but this time it'll be sine. So we take the force applied times sine of theta. And so this is going to be 70 newtons times cosine of 30.0 degrees. And this will be 70 newtons times sine of 30 degrees. Now, if you want to, you can pause the video and calculate yourself, or you can just continue watching. So we should get 60.6 newtons in the horizontal and 35.0 newtons in the vertical. That's how you solve question 1. Let's look at number 2. See, this is when I get to start drawing pictures. Okay, you can draw the picture for number 1, but I like this number 2 here. We have a gust of wind that blows an apple from a tree. As the apple falls, the gravitational force on the apple is 2.25 newtons downward, and excuse me, the force of the wind on the apple is 1.05 newtons to the right. Find the magnitude and direction of the net force on the apple. Now, we could draw this one of 2 ways, okay? But I am drawing it in the way in which I read the problem. I first came across the downward, okay, the downward force and then the horizontal force, okay? So, let's say we've got an apple right there, okay? See that dark circle right there? That's my apple, okay? That's where it started. It fell, hit the ground, and also I had a wind component to the right, okay? So this is my f of x here, and this is my f of y here. I need to figure out, how far, or with what force, the magnitude and direction of the net force on the apple. So this is going to be really that. I could have drawn it this way, okay, to where I did my horizontal and then I did my vertical. It doesn't matter. The displacement's going to be the same, but it will change what sine and cosine you use in your calculations. So anyway, what do we know? We know that we had a downward force of 2.25 newtons. Therefore, it's a negative because these are vectors, and so vectors have pluses and minuses. We also know that, this is Fy, that the force in the x direction is going to be 1.05 newtons. So, to find my net force, which is my hypotenuse, really, I need to do Pythagorean theorem. A squared plus b squared equals c squared. Okay? So, set these equal to, just like we did before, square root of fx squared plus fy squared, which gives me 1.05 newtons squared plus negative 2.25 newtons squared. And then you go ahead and solve these. You should get 2.48 newtons as your magnitude of the net force on the apple. Okay? But we also were told to find the direction. So we're going to be, where our apple is located, we're going to use that as our theta. Okay? Right here's our theta. So, to find theta, we take the inverse tangent of fx over fy. And so we get inverse tangent times 1.05 newtons over negative 2.25 newtons. We should have 25 degrees. And there's different ways you could label this. You could say 25 degrees counterclockwise from straight down, okay? But it's just, as long as you can make sense of it, that's fine, okay? And let's do number 3 here. The wind exerts a force of 452 newtons north on a sailboat, while the water exerts a force of 325 newtons west on the sailboat. Find the magnitude and direction of the net force. So it's much similar to number 2 here. Okay, so we've got a boat. Okay, sailboat. Woo. Okay. Now the wind is going to be our Fy, and the water is going to be our Fx. Okay. Again, we need to figure out what this is. Okay. And so we need to find the net force acting on the boat between the water and the wind. So get square root times Fx squared times Fy squared, which ends up being 325 newtons negative, because in the horizontal direction, remember the horizontal, it's going west. So it's 325 newtons. And the Fy, again, I forgot to label, it's 452 newtons. Okay? So that's squared plus the Fy of 452 newtons squared. And again, you can pause this video if you want to double check, but your net force should be 557.7. Oh, I can't even write with this marker here. 557 newtons. Okay. Next, we have to find the direction. So take the inverse tangent again. We have negative 325 Newton over 452 Newton. And we get 35.7 degrees west of north. And so really, again, it's not any different than what we've already been doing. Okay? So, you can double check my math, but it should be all good to go. Now, as I said at the very beginning, I promised to tell you what questions you're going to do for your homework. So, let me get myself flipped back here. So, I'm going to tell you what questions to cross out. So, these are the ones you are not going to do. Cross out number 1. Cross out number 2. Cross out number 8. So again, you are crossing out numbers 1, 2, and 8. The ones you have not crossed out are the ones you will do for homework and bring in tomorrow. Okay? So, again, if you have any questions on this, let me know. Make sure to bring in your problem bank B tomorrow to class. If you're out of class, make sure you submit it to this assignment that I'm going to be posting on Google Classroom, and then also be looking for the digital version of the quiz. Hope you all enjoyed this video. I will talk to you all later. Bye-bye.